evening, everyone. Am I audible and visible?
Hello, yes, you are.
Okay, thank you all. Once again, good evening, everyone. Welcome to day 3 of QBronze workshop from QBulgaria and QSlovenia. Before I start today's topic, following or supporting the last lecture, I would like to give 5 minutes in explaining practical steps to start with quantum machine learning using Qiskit package. At present, the Qiskit is already configured. Either that's 1.0 as per the version mentioned in the installation notebook, or 1.1 if you have followed my steps. On top of that, the one additional requirement to start with the quantum machine learning using Qiskit machine learning package is to install this one. Simply on top of the present environment, give this command to install it. For me, it is already installed, so we'll get the message the condition is already satisfied. With today's understanding and some of the additional resources discussed few minutes back, it's a time you can spend some time to understand about the quantum machine learning. One of my favorite and the most easiest resource in that one I'm just set up the book. Okay, this one. The first one is about the mathematics. Second one is the book on a small book, basically a resource paper published a few years back in, I think, 2000, 2022. And that is Introduction to Quantum Machine Learning. So let me, yeah, this one. Other resources have already been discussed in the previous lecture, and this is to give the fundamental working and the steps necessary to start with the quantum machine learning. Very nice one. On top of that, it is free to use from the internet. Let's see the title a bit slower. Yeah, once it is open, I'll come back to this one. And once that is installed, the next step is to run one simple program, which you can verify your installation by using one default program or the one sample programs given here. Either by writing your own from the scratch or to test the environment, run this example. It is compatible with the versions you install right now or we configure right now. It's good to manage in one folder. Let's say for me, this one. This is to support the last lecture and to get ready with the one sample environment to start with the Qiskit machine learning. I discussed it earlier, and and been covered about the different mapping and then the functions. Just we'll check the environment. Is it ready or not? We'll come back to this one. We'll get the result of this. This is this book. Quickly can search by taking this name online. There's an introduction to quantum machine learning for engineers. Probably we'll get the URL. Let me share that in the chat box. This one. This PDF is here. Simply click on this link. This is the one reference guide for quantum machine learning. And the second part is the steps to prepare your environment, which you can refer here. Okay, these are some additional practical support to the last lecture. Let me come to my point right now, or today's schedules or agendas. Myself, I'm Amrit Chetri, and I'm the lead and the instructor of this session. Today, we'll be covering day 3, that is 2 qubits, phase kickback, entanglement, and super dense coding, quantum teleportation, and the multiple control constructions. First, to check whether the lab is ready or not, I'll be using this. And then also to give the initial understanding what you'll be learning in this session. This is the one, quantum teleportation. We'll understand it, I'll explain it. One example at the very beginning is to send the message as created by the set of the programs first, just to check it, whether everything is ready or not. Yeah, we can see this is running perfect. You all also do this thing to ensure that the environment is ready. And this is being tested well. So environment created for quantum machine learning is ready, which is additional. There won't be any assignment based on this. If any, probably we'd cover many of the great advanced topics here. And I also explained one good resource here. Just give the name of the one good resource. Just get it and keep in your reading library. Now in 5 minutes, I'll quickly take the revision of yesterday, last session, that is day 2 session. In day 2 cover the 1 qubit system, and then the representation of the quantum state in vector representation. Today we'll be covering one more representation, that is unitary representation, which is the unitary representation of a given circuit. In revising the state, a state of a system or a quantum system is represented as a vector, and a Hilbert space is a complete vector space with some products and describes the state of a quantum system. There is another state called the basis state, which is the building block of the quantum system. A state of a quantum system or a qubit can be represented by psi, which is given like ket of psi, and it is a representation of that state, alpha ket 0 plus beta ket 1, where alpha and beta are the complex number and represents the probability amplitude, and their square magnitude or square of alpha and the beta gives the probability of measuring the state of qubit either in 0 or 1. This is a very critical statement for the beginners. In this equation, ket of psi is equal to alpha ket of 0 plus beta ket of 1. Here, alpha and beta are the complex numbers. And to get the probability of the state 0, need to square alpha. And for the probability of 1, need to square the beta. And another, there are some questions too on this one. For any qubit system N, the Hilbert space required vector space or the Hilbert space is 2 to the power n. For n qubit, it is for one n qubit, it is 2 to the power n. For a single qubit, 2 to the power 1, that is 2. And for 2 qubit, it is 2 to the power 2, that will be 4, and so on. In multi-qubit system, it consists of 2 or more than 2 qubits, and tensor product represents the state or combined state of 2 different qubits. Entanglement is possible or one of the property behaved by the multi-qubit system, and it cannot be in reality presented by a single qubit system. In other words, entanglement is the property of the 2 different entangled photons. CNOT, which is also the control gate, it is applied from one gate to another. In this one, there are control gate and the target control qubit and the target qubit. Basically, it is not possible to apply the CNOT gate. These are some of the discussion had in the second day. And one of the understanding it was about the tomography. It's the process of creating the state of a system by measurement on an ensemble of the identical quantum state. And it is also used in the quantum system forensics to understand the basic state of the system. There are some applications we discussed earlier, then characterizing the quantum state, and it is used in quantum error correction. Probably in this session, in QBronze, we don't have much on the quantum error correction, but quantum tomography is used across different requirements. One of them is a quantum error correction, and also to build quantum algorithms to reconstruct the state as per the requirements of a given problem statement, or for a given problem statement. For today, it's about the phase kickback, an algorithm, quantum entanglement, and then some simulator and some examples, taking to the basics of some of the concepts which are there in the ongoing or the next notebooks. Phase kickback, by definition, is a phenomena of quantum system, which is basically is a phenomena to transfer the state of one qubit to another during the control operation. In certain condition, the state of one qubit is transferred to the another one, and we'll look at into more details in the one of the notebook. If a state psi is an eigenstate of a given vector or a u with the eigenvalue of e to the power 2 pi I delta e, then the phase is effectively transferred to the control bit. At this stage, if there is a condition satisfied, or when a condition is satisfied, the one state is transferred to the another one. And that is primarily, and it's a fundamental level, it's called the kickback of or phase kickback in quantum machine learning or quantum systems. It is used across different applications, and these are some of them. And one of the requirement we will see is in the Gruber's algorithm that will be covering in the next session, that is tomorrow. And others are quantum phase estimation, quantum Fourier transformation, the Josa and Simmons algorithm, quantum simulation, and Hamilton evolution. And it is also used in the QEC, that is quantum error correction. There are some examples. So very first thing, kickback is the phenomena where the phase of a qubit, either down or up or its phase, is transferred to another one during a control operation. Depending upon the condition, its phase is changed. We'll see a practical example or code example for this one. Second one is quantum entanglement. As seen in the first day, it is a phenomena in which two or more than two quantum particles become correlated in a way that their quantum states are intrinsically linked. By knowing the one property, it allows to know the properties or the set of the properties of another particle or another photon. Explaining further, measuring the property of one entangled particle instantly determines the corresponding properties of the other regardless of the distance. But there is no classical analog, or there is no such classical system or the classical phenomena to represent this one. And some of the real-time application has been presented in entanglement, which were in the news, published by different uh, journals, different articles. You can check that one. Spooky actions at a distance. This was the phenomena observed and explained by Einstein to describe the correlation between the entangled particles. Some changes were suggested by other scientists later. Initially, it was given by Einstein to simply say that there is a probability, or there is always a great probability to have a correlation between the entangled particles. The next thing under the quantum entanglement is a super dense coding. Is a mechanism or is a communication protocol that allows transmission of two classical bits of any message or information by sending only one qubit. It can be explained in different way, but in one simple definition is a protocol by which a transmission of two classical instead of the quantum classical bits of the information can be transferred by sending one, because one is used or controlled by another one. There is also a one notebook to explain it, but initially it's a mechanism or communication protocol that allows the transmission of the classical bit. Instead of sending both of them, it sends a single qubit. Next, to simulate some of the uh, scenarios or to test the algorithm, there are two approaches: to use the real hardware. Another is use of the simulator. By understanding the simulator, as discussed in the first day, it is a software tool or a framework that allows the simulation of a quantum system. Another great part on it, it is simulated over the or on top of the classical computer. In future, we can see this simulation could be over the quantum systems, but right now it's always over the classical system. It is used for the quantum state simulation or algorithm testing and other works. There are different types. Four of them I've collected, and the same is available somewhere or everywhere. One is the gate-based simulators, then quantum Monte Carlo simulation, tensor network-based simulator, and hybrid. In hybrid, there's a classical and others, or maybe a combination of all three above. But what we'll use right now is the simulators or the simulation from the Qiskit. And there are other simulators. It is basically not a hardware, primarily a software or a framework. In that case, the first one is a Qiskit, then Google Shark, Microsoft QKD, Forest by Rigetti. So these are the top five, or we can say these are the best five to use. And right now we are working for the Qiskit. Next, the notebooks. 2 qubits, phase kickbacks, entanglement, and the multi-control construction. I explained most of the details. Now let's see a very simple questions and answers from the participants. The questions: this is on the chat box, or I'll be writing here to make it a little interactive, very simple. X get in 0 state, what will be the result? If you apply X get to the state 0, what will be the result? Let's see. You all please give a simple answer to it. If we apply X get to state 0, then what will be the result? Okay, very nice. Yeah, great. And some state, if you apply in the same one, if I apply the same get, but instead let me copy it, this one. This is state 0, but instead of this one, if we apply the edge get, watermark get, what would be the result? Instead of equation, can give the name of the state. Okay, you will find this one, we'll come back this one, right? Only one, there's a plus get, we'll see, we'll check this one. The first one all have the correct answer. We'll come back to that one. Only one answer there. Okay, with that one, you all find some correct answer to that. We'll be starting the today's topic, that is entanglement and protocols, 2-qubit system. In 2-qubit system, there are, as we utilize the formula 2 to the power n, if you apply 2 to the power 2, that will be 4. There are 4 different states for the 2-qubit system. The first is get up 0, 0, get up 0, 1, and get up 1, 0, and get up 1, 1. This is based on the equation that for any n-qubit system, the number of the vector representation of the state is 2 to the power n. So in that case, here are the 2 qubits, so 2 to the power 2 is the 4. So for any state, get of AB, that means the first qubit is in the state A, and the second qubit will be in the state B, and where A and B belongs to the one set of the real numbers. Now in this one, this is the very beginning. Get of 0, 0 means the first state when it's represented in a vector form, it is 1, then 0, 0, 0. And for the second one, this is a get of 0, 1, that means 0, the 0, then 1, and 0, 0. Now second one, 1, 0 is just the reverse of the second one, the 0, get of 0, 1. This goes to the third position, and then 0, 0, and 1, 0. And 1, 1 is just reverse of the get of 0, 0. So in that case, instead of at the top, it goes down. So these are the vector representation of state get of 0, 0, and get of 0, 1, get of 1, 0, and get of 1, 1, or get 1, 1. Here is a generalization for any system. If there is a k as the number, then the total number of the state for that system will be 2 to the power n. That's already been discussed. Now here, a simple program operator on 2 qubits. This is the 2 qubit, it's been defined here, and how the math get is been applied for both of them. So on drawing it, it is expected that it gives this representation or picture. These two Hadar marks can also be represented as a single system And we learned earlier by using the tensor product, it is possible to have the combined state of two different qubits. And when H tensor of 2, it's written as H tensor H. And in this case, it becomes like this. So here, H is the state of watermark that is known in the beginning. This is the vector representation of watermark gate and the tensor product, and then again the second watermark. And by applying it, the second part goes against each element, and when you multiply 1 by 2 into 1 by 2, that is becomes 1 by root 2, 1 by root 2, it becomes 1 by 2. It's quite simple. So again, the second part goes against multiplies with each of the element. So 1 by this part with first one, and the second with the whole part, whole second one, second H, and then also for the third element. Now we are going to see the representation of the gates by using a unitary simulator. And this one, there is a simulator, another simulator other than the AER simulator called unitary simulator. And it also takes the similar arguments just like for the AER. Here, instead of representing in the AER simulation, it represents as the unitary simulation, that is the number of the vectors. The first one is to import this one. Instead of AER, it has to be unitary, and then the job, just like in the AER, it has to run the job against or using the quantum circuit, and we can iterate for different set of the value. Here what is happening is simply using the unitary operator instead of AER operator used earlier. Now let's see one example here. Of AER simulator. You can see here job, then AER simulator, then run, and then the circuit. The construct is same for the unitary simulator too. Here, instead of the AER, it is unitary, and then it returns the job that has a result, and from the result can get the unitary representation in terms of the decimal. All these been represented as a decimal, and this kind of representation of a gate is called the unitary representation or unitary simulation. We define the 2-qubit system. This is one of the tasks, and they can be denoted as already known to us, that is Q1 tensor of Q0 in a cascade. So which can be something like this one. As it is a unitary operator, I is one of the unitary operator, and by applying Hadamard gate, a tensor of the Hadamard with the unitary will get the representation as mentioned here. We define the 2-qubit system, Q1 and Q2, and they are tensor in the cascade. The next part, then a quantum operator, when applied to both qubits, will be Hadamard of H tensor of I. I is here is a unitary operator. Quantum operator in the above circuit is using unitary simulation, and that is verified using the representation that is H tensor of I. So here is the one representation, the code to represent this what is called 2-qubit states. This is tasks. That's 3. Once again, in manual calculation, it is h tensor of I. I, we know that it is the matrix of 1, 0 and 0, 1, and then applying the header math, we'll get the rich state like this one. Now, this is a representation, or we'll be extracting the similar unitary representation using this code. Need the quantum circuit here. This is above. And you can see this has been represented in this form. This sometimes gives me some error. Now, next is the direct multiplication of a bit of. The next is to apply the Hadamard's or Hadamard gates to both of the qubits. Right now, we apply in this one only to the first one or second one instead of, there are 2 qubits, but by writing H0, this is the second qubit. The next one is to apply the same for both the qubits. And that can be done, can be represented in this format. And the header math, we already have seen that H of HI of the state represented like this. This is the first Hadamard gate, H tensor I, and then for the second state, there's I, a gate of 0, or that state is represented as 1, 0, 0. So this is this part. On doing that, it gives, on multiplying or on doing the tensor calculation instead of the multiplication, just a correction there, it gives me the state like this one. We can calculate the quantum state of the same one in the composite system in this form too. That's Hadamard of 0, a gate of 0, tensor, Hadamard of another state of 0. So that is again again is going to be the same. Instead of following the previous approach, can be done in the second approach. So it's multiplied with the first item. The second multiplies with also the second. So in that multiplication, that becomes 4 elements of 1 by 2. These are the 3 different ways the same has been calculated, right? This is for the H0 and H1 and other calculation. Overall calculation is same. This is for the tensor of 2 in the same state, that is state 0, 0. Second one is the state 0, 1. And third one is in the state 1, 0 and 1, 1. And by knowing any of the one calculation, it becomes quite easy to calculate the final state if there is a need of the calculation. This is for 0, 1, state 0, 1. Second one is state 1, 0, 1, 1, and overall calculation is always the final product, that is a tensor of 1 by 2, only the difference is there. The sign here it's a half 1 by 2 and minus half by 2, and this state are different for all 4 states. Once again, we started by understanding the 4 different states of the 2-qubit systems, and this is to apply the Hadamard gate to both of them, and these are representation for the 4 different states, that's at the state 1 0, state 0 1, state 1 1, and state 0 0. Next is the CNOT operator, which is used and applied to multi-qubit system, including 2-qubit system. And it changes the state depending upon the conditions that we have seen in the slide. If the state of the first qubit is 0, then the state of the second qubit remains same. So let's follow this one. In applying the CNOT gate, if the first one is 0, then it is always the same. If the state of the first qubit is 0, then the state of the second qubit remains same. 0 0 0 0. Now, if it is not 1, it is not 0, then it applies NOT gate. In that case, 0 becomes 1 and 1 becomes 0. So this is how it is calculated. A bit complex. First need to know the condition. If the first qubit is 0, then NOT is not applied in the second. If it is 1, then that is applied for the second one. In the first one, CNOT on state 0 0, the first is 0, remains same. Second qubit remains same. For the second one, it is 0, and the state 1 here, it will always be the same. Now in the second, it is 1. Instead of 0, the AND gate is applied, and that moves a change to the 1. And for second one is 1, and 1 becomes 0. Now we'll see 1, and this is a 1 control gate. So here in writing, there is a set of the pairs in 4 different states. And by creating 1 quantum circuit, we are checking if the pair in this one, every time it sends 1 element. In the first one, it is 0 0. So in that case, pair 1 0 is not 1. Here it is not going to come. And in the second condition, if pair 0, it's equal 1. Again, in this one, it won't enter here. It is going to enter this block only for this. For 1, if it is 1 for the first, this is not valid. This condition is valid once for the second, and once for second, and twice for the last 2. So this is how it works. And then once that is applied, then this is the CX gate. And after measuring twice for the 2 different pairs, the first is the 0 0, as there is a control one. Second one is 1 to 0. We are going to draw it. On drawing, it gives the state like this. Now the first one, there's a 2-qubit system, and it has been represented for 4 different combinations. This is a bit complex. By understanding this, you could be able to understand the many concepts here. The first state 0 0. For this one, we'll see this X gate is not applied. For the second one, X is applied. So how that is applied here, you can check in this second one. For the second one, this has 1. So in the second part, this is entering here. And because of that, it applies the X gate, NOT gate, to the second qubit. And this is on the reverse way. If we see this one, it is applied in the first one. By changing the reverse option here, we can see in the sequence. And for the second, it will be applied for the second, third state, that is 0, 1. Now in 0, 1, in this code, that is 1, 0, it comes to this one, then that is applied in the first qubit. X gets applied for the both of them. Now let's see why. Yeah, look at second, it's also 1 and 1, so that will be applied for. And the last one. Oh, I checked the last one. The second one, that's for 1, 0, it is only for the 1. That is true. I just got this one. For this is only for the first time. When it enters here, X gate is applied in the qubit 0. So here is the qubit. Just a minute. X gate in the state 0, 1. Oh, that had changed 0, 1, 1, 0. That is for 1, 0. This, if it is peer 1 or peer 0, in this case, the peer 0 each 1. So here is the 1, so it is going to be in the qubit 2. It's fine. And in this case, as there is both are in the state, the condition is verified here, or it's true. H1, 1, this goes here, and X gate is applied here in this one too. So in that case, it is been applied for both of them. So very simple, but very complex, and just have the greater understanding of this statement here. It is applied if the first qubit is 1, if it is first qubit, first state is 0, in that case, it is not going to apply, not get to the second qubit. Also take the this one. This is to represent the tensor of Q1 and Q0 in the Qiskit. You already did one above the calculation, manual calculation, and this is the code to represent that one. And solution is here. This is the task 6. Just like that, the set of the 4 different states, and then applying the same logic here, and then applying the Hadamard gate to both the states, that is state 0, qubit 0 and qubit 1. And this is a C0 gate, a CX gate for the gate qubit 1 and qubit 0, but in the reverse way. And then again applying the Hadamard gate, and then doing the measurement, and when it is measured, it becomes like this. Here also the state for 4, the representation is for 4 different states. To understand it, our circuit has 2 qubits, that's qubit 0 and qubit 1, and we are going to calculate in this one that the program calculates the tensor of Q1 tensor Q0, and these are the sequence of the steps, applying Hadamard gates to both the qubits. And it's already said that applying C0 gate in this sequence, that's why this is one statement here. And then again applying Hadamard gate for both the qubits, and that is again Hadamard gates here, and then measuring both of them. Both of them means the here C and QC are the classical and resistor, and then creating in the reverse way. If you remove this one, if you make false, then instead of 1, that becomes 0. This has been done. I think it's been discussed quite in details. So just do the thorough go through these go through the notebooks. Next is the phase kickback. It's a conditional change in the phases of the qubit. On applying the control NOT gate, or when we apply the control NOT gate operator, the controller qubit will be affected. That means it is not always affects the all qubits. In this sense, when you create a circuit with the qubit 1 and qubit 0 and reading the order of the order of the qubit in the cascade, it can be applied or can be done by applying the logic in the qubit, first qubit, a second qubit, and then again in the first qubit. That means on applying the Hadamard gates. And when you apply the CNOT operator, where the controller qubit, as discussed, CNOT gate is the multi-qubit operator. It is applied or it is used in the 2-qubit system. In that case, when the controller qubit is the Q1 instead of Q0, and the target qubit is Q0, in that case, it changes the state of the second one. And here, the steps. The first one is applying the Hadamard gate to both the qubits, then applying CNOT gate where the condition is this one, then again applying the Hadamard gate to both the qubits, and then doing the measurement. Basically, this is also the extension of the previous program. In one sense, in control operation, when the condition is satisfied, the state of the qubit is changed. So here, the next is the effect. So we'll check the quote here. The same condition in this one, first Hadamard gate, then the CNOT, then applying the Hadamard gate in both, and then measuring the outcome. So instead of taking all the states, this is for in the previous one. Instead of that one, here we have created, the program has created 2 classical register and the quantum circuit. That means the 2-qubit system or the 2-qubit quantum state. And then very first is we start for the state, the very first one, 0, 1, that is set the state of Q1, that means the second qubit to 0. So how that is done? By applying the X gate. Once again, just be making clarity, adding clarity on following this statement to change the state of the Q1, the second qubit, should apply the X gate. So here is the X gate to the second qubit. Above. Yes. Yeah, okay. The first qubit is being treated or applied with the X gate that changes the state. State to 1, as in here. Then before measurement or before applying the another gate, here is a barrier function, and then applying the edge gate again to the same qubit, that's the qubit 0 and the qubit 1 together. And then the CNOT gate, this is the 2-qubit gate. So here is a 1-qubit operator, only 1 qubit is given here. But for this one, there is a 1 controller, another one is the target. This is the controller and this is the target. And then again, applying the Hadamards to both of them and doing the measurement as given above. This is for the state. We started with the state state 0 for here, and then, oh yeah, 0. And then, yeah, this is, this changes the state of 0, 0, then we got this uh, condition as it is applying the control gate, the state of the second being changed, and the overall uh, overall overall bit string is 1 1, and then the out of this 1,000 the overall starts here. If we give 1024, in that case also probability will always 100%. It is 100%. Now, next is to understand the effects of the CNOT gate. The first one is the initial state of a qubit before the CNOT is applied. This is the state of state when the Hadamard gate is applied, then that takes to the superposition state. And the second one is on the same state. Let's check that this is the initial state. That's 1 by 2 gate of 0 plus 1 by root 2 gate of 1. And then when CNOT gate is applied, it changes the state and it becomes minus 1 by 2. The phase has changed here. So this is the effect of the CNOT gate, and this phase change, it's carried out to know the different different algorithms, or is used in the different algorithm. One of them such application is in the Gruber's algorithm. We'll see in the next lecture tomorrow. Once again, on applying the CNOT gate, the state, the phase had changed here. Initially, it was 1 by root 2 gate of 0 plus 1 by root 2 gate of 1, and it had changed. The other value in a plain explanation, if you look at into the other values, they are same, but the phase had changed from plus to minus. The quantum state of a composite system, as seen, it's denoted or represented by tensor. So in that case, by applying the tensor to the both the state when the CNOT gate was applied and when CNOT gate was not applied, can be represented in this fashion. 1 by root 2 gate of 0 plus this, and then the tensor for the first with the second one. Now here, one condition. CNOT affects when up qubit has a value of 1, so which is based on the understanding in this one. If it is 0, it is not affecting. When the up value is 1, then in that case, the phase had changed. With this explanation, you will be able to understand on going and looking into the notebooks after this session. We discussed this. Now let's see this task. The task is to create the 7-qubit system. That means starting with 0 to 6. This is the index. Then next is setting the states of all 6 qubits to 0. Then set the state of the bottom qubit to 1. There are up qubits and the bottom qubit, top qubits, and then the bottom qubits. For the top qubits is to 0, and for the bottom qubits to 1. And the second, after applying that, next is applying the Hadamard operation to all the gates. As this is a single qubit system that can be in the loop. Then applying the CNOT operator in this order. Control bit 1, target bit 0, control bit 4, target qubit 0, and control qubit 5, that's the sixth one, and then the target qubit 0. So here is the implementation for the above statements. The first is set the here it is X. This is to set 1 for all up qubit, and up qubit initially is in the state 0, then by applying this it becomes 1. And the second one is applying the Hadamard gate to both the qubits 0 and 1, where control qubit is up and then the target qubit is down. So this is the initial understanding we met in creating the circuits here. The next is in this one. Next is again applying the Hadamard gates. And this condition right now, this is probably the second one. Yes, second one. This was already discussed. Again, there's a quick revision on that. And on applying that, it gives the state like this. This is again one simple revision. So next one, we are looking into the next one. So in that case, the similar one, but the overall conditions are different here. Once again, applying the Hadamard gates to all the qubits in the first part. So let's check that one. So here also the circuit, and then the first one is applying the X gate to change the state to 1. So we already learned that this by applying this, it becomes state 1, and then creating a barrier here. And now here applying the all Hadamard gate to all. So what is the meaning of this? This is 0 to 1, and this is in the loop. So it goes from 0 to 1, first 0, then 1, then up to 6, applying to all. And the next is the crucial part, but that has to be done as per this condition. 1, 4, and 5 control gate. Target qubit is 0 only. So 1, 4, 5, then again barrier, and then applying again the similar one here to this one too. So quite simple. Again, applying the barrier and measure and then draw. Once you draw, to get the final bit string, can apply the AER simulator instead of the unitary simulator. We got this one here. The bit string, it's all 100%. The probability of getting this state is 100% here, and that is the expectation because this is the implementation of the given C0 gate. And in looking into this example, check this condition, follow the steps. Only the complexity is here to apply the X gate to change the state. Next is to define the barrier, and then applying the Hadamard gate to all. Then this condition is simply given above. Again, applying barrier here before applying the Hadamard. So this is the rule here. And then measure. And after measuring, simply display. Quite simple. Only a bit complex later could be in understanding or writing your own. My way or my suggestion here, simply write for the one C0 and then check the outcome. Again, write at the second one and check, and so on. Started, I think, yeah, I'll be able to finish. The entanglement. Here, now we'll understand about the entanglement. Before starting the entanglement, let's revise this one. Entanglement is a phenomena or quantum phenomena in which two or more than two particles become correlated in a way that their quantum states are intrinsically linked. That means when two photons or two particles which are far distant or as a distance, when they are linked together, that state is called quantum entanglement. And here, the first one, it is about the ESA and the Balvis. Both has the state at zero, that's initially it is in the zero state. ESA applies the Hadamard gate to her qubit. This is the rule defined in creating entangled state. The quantum state of both of them, basically, when Hadamard gate is applied, is superimposed in this one. And then the ESA and the Balvis combine their qubit by using, but here, Balvis hasn't applied the Hadamard. So in that case, the state 0 is represented by vector of 1, 0. And on multiplying, it becomes the initial, we can say the combined or the tensor state of both the state of ESA and state of Balvis. Balvis hasn't applied the Hadamard gate, but Hadamard gate is being applied in the ESA state 0. When they are tensor, it gives this state, and which is by the rule that learned few minutes back, which is the tensor product. And in calculating the tensor product, how it is done, the second goes over the first one, then second goes over the first element and the second elements together. So this is the state. Now the second part is ESA and the Balvis apply the CNOT operator on two qubits. So CNOT is this one, and when this is applied to their state, combined state, it becomes the state that is 1 by root 2 gate of 0, 0 plus 1 by root 2 gate of 1, 1 or gate 1, 1. And this state, at moment, Balvis and ESA are correlated each other because initially both of them has the state 0, and then on apply Hadamard gate and tensoring both of them, they got the state, and applying CNOT gate, they reach the state where they are entangled each other, although they are in the far distance. So here, the quantum communication been represented in this picture. So where initially Balvis and the ESA has both 0, 0 and Hadamard take that into the superimposed state, and then when that was tensor, they got the state, and then finally that is being encoded as a part of the encoding mechanism discussed above, and then finally that was sent to the Balvis, and on reaching that, that is decoded again by using the same Hadamard gate here. There are other operations, but one of the operations here is the Hadamard gate. This is a bit complex, but I think by knowing this, it becomes quite simple. So steps are quite simple here. The same is used in the code too. After communication, both Balvis and the ESA has both the qubits. I mean to say their qubits. Balvis applies CX gate, that is CNOT operator, where CX qubits is the controller. So this is one of the key points here. In classical cryptography, we use the similar mechanism. Private key is used for decoding. So here also the ESA qubit is the private key, and it is used for a controller here. And then Balvis applies S gate to the ESA qubit, and Balvis measures both qubit. The measurement results exactly the state of A, B. A bit challenging, but it's quite simple to understand this one. So verify the correctness of the above protocol. So these are the statements given here. We'll check to this solution. As I have a little constraint to explain those details, I just want to get into the code implementation here. Again, these are the different conditions given here for the pair A, comma B, and that belongs to the 4 different states of A and B. Here we can say A and B is already in the state, that is as we see in the vector representation of any state 0 and 1. And the very first, the pair, because that is for the 0 and 1, this is the pair to represent the 4 different states of initial of 2 qubit, qubit 0 and qubit 1. And the next is for all pair, it is applying C NOT gate. Before that, there's a Hadamard gate to the 1. That is, as discussed, that is to the ESA and the sequence. So that is been applied to the ESA qubit here is mentioned here. I was checking the sequence and then applying the C NOT CX gate or C NOT operator to the ESA qubit. And here there is qubit 1. It's the ESA qubit, and qubit 0, which is again the Bavis qubit. So controller has to be ESA, and then the target has to be Bavis. And then again applying the JET gate. As I said, there were other operations, and that operation is JET gate, and in JET gate is being applied to the Bavis ESA qubit. And the next is checking if the pair has a bit of 1. In that case, again applying the X gate to change the state from 1 to 0 or 0 to 1, and then applying the barrier, and then again applying the C NOT gate. In this one, the order is again the same. This is CX gate to the controller is of the Balbis, and then the controller is ESA, and then the target is Bavis, and then finally the Hadamard gets to the Bavis. So in that case, the final representation of this circuit becomes this. There are 4 different states, and they have been represented in this one. So by understanding the first one, so how the 2 qubit system can be operated, or the operators can be applied to 2 qubit system, this becomes quite easy. The next one is, can the above system setup used by Balbis verify the following modified protocols? Some changes have been added here, and the sequences has been given here. So the goal is to check this condition. So quickly by going here, this is the check for this above condition. Some changes has been added in this statement over the first one, and by checking and by applying those changes here, we just want to check whether it gives such state or not. So here also the final state is the same. Here the bit string 11, that is the number, the 100% probability. So here also the 100% probability. So the changes are the correct implementation in both the representation of the pseudo codes. The next one is quantum teleportation. I mean the same, yeah. Quantum teleportation is the mechanism or the quantum phenomena of sending 1 qubits from one to another one. On defining it, if we have to see, I've done earlier, if we use that's 1, to get more details. It's a fascinating, whatever that one, where the state of a particle is transferred from one location to the another one. Now, this is a quantum phenomena which transfers the state of one photon or the particle from one state to the another one. So other details are here. We are not going to check on that. So what is here, it's about transfer of the particle or the state from one to another one, or from one location to the another one. Now, these are the protocol mentioned here. The protocol uses 3 qubits as defined below. Qubit 3 or qubit 2, qubit 1. The qubit 2 is the ESA quantum message, and qubit 1 is the ESA qubit for entanglement. And then Q0, as seen in the previous example, is the Balvis qubit. So there are 3 different ones. One for entanglement, that is Q1, and the last qubit, or the last bits, not qubits, the last bit, last qubit is for the messages. Qubit here because is the quantum system. So these are the sequence to understand. The first one is ESA has 2 qubits and Balvis has only 1 qubit. And ESA is sending the message to the Balvis, and this is about the teleportation, means sending the message by ESA to the Balvis. ESA quantum message key is Keta B, which is the vector of A and B, and represented at this one. The entanglement between the second qubit of the ESA and the qubits of the Balvis, it's this which we calculated in the last section. When the tensor is created, it gives this state. So quantum state of the 3 qubits right now could be different than the 2 qubits. And this becomes the final qubit, as the state is, the key is being considered Keta B, which is A and B. So in that case, the combined state of the 3, or the tensor state of the 3, would be 1 by root 2 A, Keta triple zeros, and others in the sequence. Now, just like earlier, one of the operations to apply here is the C naught operator. Once again, this is on the sequence we applied in the previous one, where only 2 qubits were there. But in this one more qubit to send the message from the ESA to the Balvis. Now, on sending, ESA applies Hadamard gate to the qubit 3, or the third qubit, which is the message to send. And calculation has to be done, and doing the calculation, quantum state can be or have been represented in this form. So which is again based on the key defined here, which is the vector of A comma B, or AB. It's a bit difficult here, but let's make it more clear by looking into the quote example here. But I found it quite clear to all that the state and the sequence are quite clear here in the notebook, as well as in the beginning representation too. Q2 is the ESA quantum message. Q1 is the qubit entanglement for the qubit for the entanglement, and Q0. Now next is to know about the sequences in the coding part. So in teleportation, the very first one is this is on applying C naught gate to the combined state. And these are the 3 qubit system. There are 3 qubits. Oh, there's an initial understanding for any 2a to the power n qubit system. The number of the vector representation is 2 to the power n. So here it's 2 to the power 3, 2 to the power in that case, the vector number of the vector representation. And here we are talking not the vector representation, but the states. So these are the different states being considered here. And this is not the combined state of 2 to the power n qubit system. This is the combined state, or those are not the representation of the state of 2 to the power n system. Here, these are the composite state of the 3 qubit system on applying the given operator. What I mean to say, these are not the all states of the 3 qubit system. These are the states of the 3 qubit system on applying the operation in the using the CNOT gate. Now solution here, CNOT gate is starting with the controller Q2 to the target qubit Q1, or the third to second one. And on doing that, it converts the state that is 1/2. It makes the state like this one. When the CNOT gate is applied, you know the condition that if the first qubit is 0, then only it changes. So in that case, whoever has 0, that has become 1. Second part, calculate the new quantum state after Hadamard operation. So in the 3 combined state, by applying Hadamard gate, that superimpose, in doing that, need to tensor the whole element using the quantum vector representation of Hadamard gate. So in doing that, it gives the state like this one. That calculation a bit complex and the longer one. And final output is going to come this one. And the way it is done, it's applying the Hadamard gate to this state. And Hadamard gate has the vector representation, that vector representation, and the tensor of the given state. This is now you can see here on applying the Hadamard gates, these are the state before applying the Hadamard gates, and achieve in this one, on applying the C gate, and the next Hadamard gate, it makes this. And the task 3 is again ESA sends the measurement outcome to the bulbs using 2 classical bits X and Y, and it has a key that is keta B. Now we have the value that is alpha keta 0 plus beta keta 1. So this is the in other words, to obtain the messages for each X and Y, this is the classical bit message. Balbis applies the key that was initially we discussed at the top, that is the key to get the message. So these are the code representation for that one. So here also, initially started with the state created by Hadamard gate for the bulbs for the CESA, and CESA is sending to the bulbs. And in that case, we started using the 3 qubits here, and this is the implementation of those understanding in the code. So here, 3 qubit system is been created, and the messages of some theta has been calculated here. And after that, this is basically to know the one cos theta for value alpha and beta, which is the key, or which is the operators the bulbis is going to apply to get the final message. And then again here, rotation gate Ry is a rotation gate for this given angle, and then Hadamard gate for the second qubit, and the 6 gate CS gate, control gate for the controller second qubit, and the target is the first one. So again, this is for the third one to the second one. So these are the sequence to be followed in writing the code. So it is nothing like that. It has to be this first and this. These are the sequence to at least to apply in this sequence. So for that, these are the some pseudo tasks, a pseudo statement of these tasks to follow. This all code has been written as per the task given here. And then classical outcome, these are the vector, these are the one list has been created here for the 4 different states, and then the other operations. The classical outcome, it's 0, 0. The new quantum state is being created, that is get 0, 0, and then the new quantum state get 0, 0, and then again they have the different classical messages associated with that. So by using this one, the message is transported from one qubit state to the another one. A bit difficult, but find some interest to get and deeper inside it. And then also feel open to write in the Discord channel. The second part is implementing the protocol, including the above understanding, post-processing done by the Balvis, and the measurement done by the ESA before that was sent to the Balvis. And what he did, he applied the X gate or Z gates depending upon the measurement result. Here different gates, the conditions were given here. Right now we're not in this one, so the next. And on that condition, it is calculating the final message to be sent to the Balbis. So let's check that one. In understanding this code further, the first part is the import that just fine, then creating one radians in the random order of 100, and then creating the cos and the sine for that one, those theta. Theta has been randomly generated here. And the next part is printing this one, the angle which has been done here. It is 212.4, and then the another one is 3 point. This is the radians once they are converted, and the value of A and B has been transformed to this value. Once that is done, next is applying the rotation gate for a given with the given angle which is being calculated above to 2 times the theta calculated here. This theta is this one. And this is for the third one. Third one is the message to send. And then creating the quantum state between the qubit 1 and the qubit 0. That means our first and second. By using this one, this is the basic way of creating the entanglement to remember or to learn. By applying the Hadamard gate and then again applying the CS gate creates the entangled state between 1 and 0. And the next is applying the C0 operator with the message with the messages created, and that is by the ESA on her qubit because she is sending to the Balbis. So in that case, by looking into this code, the rest of the section becomes quite easier to understand. Only the one great conditions to understand here is this one, to create the entangled state by applying Hadamard, then the CX, and then applying the condition for creating the CX gate that should be in the ESA message qubit, that is Q2 is a control gate, and then target should be the one that's her own qubit. The Hadamard gate by the ESA, and the second one, that is the message, as whatever been applied to this one, and then barrier and the measurement. And then now next is processing done by at this state, we consider it has been sent to the bulbis. And once that is reached there, next is a conditional one. If see this condition here, X gate is applied to 0 if the classical bit is equal to 1. So this condition can be written in this label. This C underscore F is the classical bit is 1, or C2 if 1, then both case, if it is 1, if the second one is 1. So if the first classical bit is 1, in that case, that is X gate. And if the second qubit is 1 classical bit, in that case, that is Z gate. So this is the operation to be done once received by the bulbis. So this is one example of the teleportation. Now, next one is the multi-control construction. This is a short one, just the further explanation or the further notebook on the previous explanation of CNOT gate. By this time, it is quite clear that when CNOT gate is applied, NOT is applied to the target qubit. The qubit is in the state 1. If it is 0, that is not applied. This is the one statement. NOT is applied only if the target qubit is in the state 1. Now, what we can think of by applying this one, in which the NOT operator is applied if the target qubit means what is the state if the target qubit is in the state 0. So in that case, it will be different than this one. This is the initial condition. We already have the understanding that CNOT operator is applied to the target qubit because it has the target and then the control qubit. If the control qubit is in the state 1, if the first one, that's the control qubit, is in the state 1, but what would be the state if the control qubit is in the 1? So this is the representation. So overall, the state has changed here. Now to create that one, first to apply the NOT to the control qubit, then applying the CNOT to the operator, then applying the CNOT operator, which needs both the qubit 1 and qubit 0, or first qubit and second qubit, then applying the NOT to the control qubit. In this one, the NOT qubit is being applied to the is being applied twice instead of once. This is the simple representation of that one. First is import, then creating, then the X to the first second one, and then the CX to targeting the first qubit, and then returning the control qubit to the initial state by applying the X to the second qubit, and then creating the unitary representation of the same. This is based on the one of the program we created with the multiple condition to check different states, 4 different states, and then if it is the first qubit is 1, and then apply the X gate or Z gate, X and Hadamard gate. On applying it, it gives this unitary representation of this state. Just like CNOT gate, there are other gates too. That is control NOT operator. It is also called the Toffoli gate. Control NOT operator is called the Toffoli gate. So in that case, it needs the additional bit. Is a 2 times control gate and then NOT. Instead of 1 more has to be added for the second C. That stands for the control NOT operator, which is controlled by the 2 qubit. Instead of 1 qubit, it is controlled by the two different qubits. In the C0, the control qubit is only one, but here it is just one. This is the control qubit. In case of C0 gate, CC0 gate, which is also called the control not gate, and in short, it is a Toffoli gate, which is controlled by the two qubits. The implementation of the CC0 gate in Qiskit can be something like this one. So let's check the quote here. After applying this all gate in the circuit, it should like this one before coming to this one. Circuit, then the CCX, that's the CC NOT gate. X stands for the NOT gate. X is simply NOT gate, and CCX C NOT gate, and the CCX the control NOT gate. Control qubit 1, control qubit 2, and the target qubit. There are 3 qubits in the CCX. And the name is the Toffoli, and then the in representation, it is a CC NOT gate, that's a control gate, and that is instead of CX, that is CCX. And this is the operator, which has a vector representation of this complex one. This is a vector representation of the Toffoli gate. It's quite difficult to remember, but one of the great way is this representation up to here, it is in the diagonal 1, 1. And then the last block, it is diagonal in the reverse, rest is 0, 0. All very simple. It's 8 by 8 matrix, diagonally 1, 1 up to the second last, and then the last one is in the reverse order, and the rest is 0. So quite easy to remember in writing it in some calculation. Implement each of the following operator in Qiskit by 3 qubits, as needs the 3 qubits to control and 1 target. Verify our verifying this implementation using unitary simulation to get this different step. So here you can see that the first one C0 C0, that is the first one, then the C0 C1, then the C1 C0. These are on the different states. And this is the implementation for the same. By giving here 0, these are the states. The C, let me explain by the quote here. This is C0, C0 not operator. So in this case, this is 3 qubits because first 2 has to be the control. So here, applying the X gate to the second and the first, and third and the second, and then applying CCX, keeping the target qubit at 0, the first qubit, and then again XX, that is in the same sequence. And that is the meaning of the C0, C0 here. That means the X in both of them to qubit 0, which is in the state 0, and the C0, again, that's in the C0. Yeah, that's the order to be followed. And the next is applying the unitary operator to get the states being created or transformed by these operators. This is the unitary representation for the C0 C0 NOT gate. That is, both of them is in the state 0, 0. Means applying the C NOT gate, Toffoli gate to the state 0, 0. The meaning of this C0 C0 is applying in this. If you have to change, then can apply the apply the X gate in the initial state. But here, instead of that, it is to know the unitary representation of C naught gate in applying to the state 0, 0. Now, next one is doing the same, but the second one is 1. So let's see that representation here. It is to apply to the 0, 1 state. And this is for 1, 0. Now, this is a one task to apply or to create the control gate or C not gate. So as suggested, if there are 3, there should be 3, not 1 is 1. So here 1, 2, 3, 4, this needs 4 and not 1. In that case, 5 gates, right? Quite easy calculation. If there are 3C, then 3 qubits for 3CC, that is control gate. So in that case, 4 control qubits and 1 target. So this is the implementation here. First is creating the 5 qubit system and then applying the CCX, keeping the target in the sequence. There's a fourth is a target, and then the second and its immediate bit is the control is the fourth one, that is the last one. There's a fifth element, fifth qubit, and then the second last, that is the fourth qubit, and the same order. So by running it, we can see this instance. The first one is applying the CCX, is in the reverse order. So if we convert this to the false, then that becomes quite easier to understand. This is from the fourth one. Yeah, this is to the fourth one. There's the AEX in this one, so can check this one, AX1. This is the fourth one. Yeah, from fourth one to the qubit 3. And the second operation is from the second to the first one, that is the auxiliary here. This the second one to the first one, Q0 to Q2, Q0. This is the Q2 here. Yeah, Q2 here. Yes, Q2. Yeah, okay, fine. And then on measuring this, it gives the state. So here also the probability is not being calculated because this is simply the representation and not the vector unitary representation. So here the probability in this one is being calculated, even not here, just the presentation. Wherever probability is created, in that case, the overall implementation of the given gate can be determined by knowing the state of the two system. Two system means the system that has been used or considered to apply those gates. Now next is creating some a similar kind of a gate and then checking its implementation for the correctness. As said here, thus executing this circuit on every possible inputs to verify the correctness of the implementation experimentally. This is what I mean to what it meant to say that this condition, the operator designed above, this is the operator we applied here. That is how this one has created the 4 qubit controllers. and this have been used here to check their outcome. Input and output, as this is the input, and then the state has changed only if has, again the not has to be there, should not get changed. The 0 is 0, 1 is 1, and that is depend upon the first one. So it's not that simple only for the C not that condition, but on applying it, the output is slightly different, and that is completely controlled by the 4 qubits instead of just the two qubits or the 1 qubit. Repeat the task operator for this one, and here there are the different steps being considered instead of just the C0, C0. Here, instead of C0, C0, there is a C1, C0, C1, C0, and the NOT gate. What is the meaning of this one? NOT operator is applied to the target qubit if the fourth qubit is in the state. The meaning of this one, if the fourth qubit is in the state of 1, 0, gate of 1, 0, 1, 0, 1, 0. So the meaning of C1 is that one. This operator works or applies to the qubit which has the state, this one. So in this, we also see one understanding here, C10, that means applying this to the state 01. The same concept here. Applying the above gate only if, where it is, only if the state is 1, 0, 1, 0, and this one. So this is how it's been implemented here. That has to be the 5 qubit system and the X to the first one. Now only the condition here is to apply this one. That condition, checking the state. QAX, this is to check the condition 1, and QX, there's a condition 0, and similarly in this one and this one. And this gate is applied only for this valid state. For this state. The second implementation is to execute the circuit to give the different inputs and then checking the correctness for this this implementation, checking them by supplying all condition here by appending the state and then also representing them as the simple outcome instead of the binary instead of representing as the unitary step representation. So here is the outcome, which is also verified for this one. The last one, writing a function taking the binary string. These are the different binary string B1, B2, B3, and B4. And then repeating the task 2 for the operator where B1 and B2 are the bits and not the operators. Where the B1, B2, B4 are the bits and not operator is applied to the target qubit to this state. The similar one, but to check the state of the second one has to be, second qubit has to be 1, 2, 3, 4. Now this state is being represented as per this one, depending upon the state of this one. If it is 0, this have to be 0. If it is 1, if it is 1. In this representation, it gives the outcome like this. There is a function here. That function is for not. It's not been called. It is taking the state or the control state, which all are in the state 1. And it also allows to check for the other states. as being the four qubit system, it can take any valid qubit state here. This is a representation, and this is the final state. With this much for today's session, and now one thing to check is the project. The very simple one, that is the second one, the swapping quantum state. First do this one, and then those C0 and other gates has been discussed quite thoroughly. And then also the quantum teleportation, look at into them to take them to the proper understanding and practice in the sequence. At the first time, you understand each of the code and then practice. And then second section, move only if the first one is clear. Just a one-word suggestion on that one. The final goal is to give an attempt to create your quantum simulator. These are some projects. Just understand and then try to apply. If possible, can do it within the given work, within the given deadline of the assignment. But these are the projects. So we'll try this one, or you all try this one. What have to be done is this test statement. It is said that please do not use quantum programming library or any scientific library such as NumPy. Use the real number and all angles in the radian, then each qubit is state in 0. This is for creating one simple simulator. And then creating the class, that is quantum program. It takes the number of the bits or qubits, not the bits, but the qubits, and the simple functions. The number of the qubits should be specified when creating the instance, this one. And then design the quantum circuit for this program. Methods. Single qubit that are applied to any specified qubit. These are the different ones. Simple, very simple one. Only the complexity is to create the one class and the qubits. And the class has already been, this program has already been done. And the method for simulating the circuit, read unitary, read state, observing the probability, execute. And very simple. An extra thing can be done. Right now, focus on writing this class. Let me explain how you can do. Simply create this class, a Python class, that takes the number in the constructor or in instantiating its object, and then create the quantum circuit to apply these gates. And the quantum should be more than 2, as it is taking C0 operator or applying C0 operator. If only one qubit, always mention in the beginning that has to be 2 qubit system or more than 2 qubit multi-qubit system. Yeah, that's why. Just give a try on making this simulator. This is not a mandatory thing to do, and we'll try to see one sample code in the next session if there are some free hours, a few free minutes from my side. There are others, can check in this one, implementing quantum teleportation. Also take the help of the other mentors. I do request all participants to send some queries to the mentors for getting some help, even for this one. Here the Python class, there's a quantum teleportation, and then add this one. It is just to simply apply the understanding in the one of the teleportation class. Just put those codes with some modification and some understanding and the meeting the requirements given here. Okay, will this much for today, and thank you Maria for arranging this session for me to speak to some of the best participants. And yeah, this much for today. Thank you all.
Thank you, Dr. Chetri.